different IP address. So you send a request here to this to this name server for one IP address, you will receive a response from another. There is the situation, this happens when there is another resolver here, there is a forwarder, and it sends the response. Of course, this will be ignored by the resolver because the IP address will not match. But the point is that I see a lot of misconfiguration on the name server side. Now, actually, I'm here to talk about privacy, so how all of this is related to privacy. It's related to privacy in the following way. So when we talk about end-to-end encryption, we talk about encryption from end to end, or at least from the resolver to the name server. Now, when you have these third-party caches operators, you cannot do end-to-end encryption. You would do encryption to the third-party operator. Now, the question is, do you trust this third-party operator? According to the attacker model, these third-party caches are not trusted. They're often operated by some organizations. They're located in different ASs than the name servers themselves. And this contradicts the adversarial model for encryption of DNS. So how do you handle this? If the resolver insists on doing encryption, how will it do encryption to the name server? It will not be able. Another solution is you can put the key here on the resolver so that it decrypts the request and forwards to the right name server. By the way, notice that these resolvers, they often serve many name servers. So if you send it encrypted, they would not know to whom. And there are different extensions that could be used, but it's not trivial and or straightforward. And so end-to-end encryption would be difficult for some encryption proposals. This is something that needs to be considered, of course, when designing defense for DNS. The configuration and architecture of the DNS name servers is very critical for encryption. Okay, and finally, protocol support. What do I mean for protocol support? So many of the proposals assume a TCP. A TCP, as you know, DNS can run over UDP and TCP. And when DNS packets, datagrams exceeded 512 bytes, to avoid the overhead which TCP introduces. And there was a folklore belief that TCP Rupert Very signed that this overhead is actually not significant if you can pipeline queries and do other nice, neat tricks. See the paper, this is in Security and Privacy. Okay, so then there is this effort to actually deploy TCP for DNS, and it seems that this may work well with respect to latencies and overhead. But there are problems with respect to support of TCP. So there were studies by such as Jeff Huston, which showed that on client side there is little support for TCP for DNS over TCP on the client side. I did a study of TCP support in the name servers, and I found challenges as well. So there are many failures. Some domains do not support TCP, but there are not so many in popular domains. But there are many failures with TCP. So when you send a TCP request over TCP, you will see often server fail, timeouts, reset packets in the middle of a connection. And this happens both on name servers, which are not behind server-side caches, and also name servers behind server-side caches. So the point is, this requires careful study of the state of adoption of TCP, whether some things need to be tweaked or patched or upgraded. Because if you currently try to run DNS over TCP, the attacker can easily downgrade this to UDP. You will not even distinguish between a failure on the name server side or an attack by an attacker who just blocks TCP doing low-rate attacks, for instance. So this is significant because if someone tries to do encryption over TCP, and if encryption over TCP doesn't work, would downgrade to UDP, this of course exposes to devastating attacks. So here I will show you some of the error messages that I collected of our failures for TCP. I have a list of those. This is a study of 50K Alexa, and it doesn't contain the number of servers which fail, it contains the number of distinct failures. And not all of them, so I found 21 different distinct cases, and name servers fall within this distinct categories. So what you would see, often you open a connection, everything goes okay, the server sends in ACK, you send a request, server will send a reset packet. You repeat that, you see the same behavior, you do over UDP, nothing is wrong. Everything works okay. Or the server will send server fail. And here are examples for selected domains which do that, and which exhibit the behavior which is mentioned. So for instance, as you can see, actually one is in Hessen, I'm now in Hessen. So after TCP handshake, DNS request is responded with a reset, and you can see this is one of the servers of the state of Hessen in Germany. If there are people from Hessen, please look into that. And many others that are in Gulf domain and so on. So this is, I could not put all of them here, so I just tried to condense, but this is a work in progress which I plan to submit soon, and I will be happy to distribute this as well. If anyone is interested in all these failures, this work focuses on problems and challenges in adoption of basic protocols like IP and TCP and UDP. Okay, so to conclude. First of all, no doubt encryption is important, and it's very important that there are people within the communities, within this community who care and who spend efforts to design defenses. This is very important. I'm not here to say this is bad. I'm here to say this is very important, but there are some things which need to be considered, such as existing infrastructure, configurations, challenges, different obstacles which may arise when adopting a defense. I mean, what good would it do if everything is adopted but then it doesn't work and then you have to change? When you change, people get irritated, annoyed, and it's much more difficult to convince them to adopt the defense. And we saw this with a number of other mechanisms that were proposed. Actually, I did some attacks on DNS some time ago, and one of the criticisms was, well, I'm attacking DNS because it's deployed, and that makes most impression. Why don't I work on something that is not deployed? This is why, in this case, I decided, okay, I'll focus on something which is not yet deployed, and then I will provide recommendations how to do it right. And that's the purpose of this work. So the goal is to show a number of important issues, and I think that it would be very important for the community to consider them, to discuss them, and to see how they should be addressed. What about third-party service providers? So some people told me, yeah, we don't need this third-party DNS operators, let's get rid of them. So first of all, there is a reason they're there. You can ask yourself, why would people adopt a cache before a name server? So there are many, many attacks against name servers which exploit vulnerabilities in operating systems, in the DNS software, and so on, where attackers are able to obtain a shell to the name server and inject records. By having this cache installed in front of the name server, the attacker doesn't know the IP address of the name server, so you never can access the name server directly. All the communication is done only to the proxy. So the name server is protected. Denial of service attacks. The name server is also protected because all the queries are sent to the cache and responded from the cache. This significantly reduces the traffic to the name server. The resources that it requires, name servers do not have to upgrade their infrastructure to facilitate many clients. And when you have this third-party operator which says, I'm an expert, I know how to run DNS, rely on me, let me provide availability and security services for your domain and for your name server, this is a good idea in general. And indeed, there is an increasing tendency to do that. So getting rid of proxies may not be so critical or even wise. I mean, I would look at the CDNs. I mean, this concept of having proxies in caches works, but we need to see how do we adapt solutions that we design for those proxies, for the existing infrastructure. We don't trust them. Do we trust them? Do you have to be, in order to become a proxy, do you have to go through some standard procedure which will qualify you to be a proxy or certify you? Or can anyone run a proxy? So questions like that. But getting rid of proxies would be difficult because, as I said, I see an increasing trend of using, configuring domains to use proxies before the name server, on the name server side, so like transparent proxies. Another question is support of basic protocols like TCP. Which version to support, which implementation? There are different TCP implementations. Sometimes one is better than the other, more efficient, maybe more suitable for the proposed defense protocol, like for encryption. Also, how do you force or enforce adoption of TCP? TCP was proposed ages ago. It was like before I was born, I think, but it's still not deployed. So there are some challenges with that, and people should look into that. So adopting TCP is critical not only for encryption, but in general. Indeed, it prevents many attacks, or at least makes them more difficult. And side channels. When designing a defense for a specific system, you need to also look in it not in an isolated environment, but actually part of a system. So the side channels were known to be lethal for web, and there were studies which showed that by looking at different prefetching or looking at the object sizes and timing information, one can even learn the input of the client to a specific website. That was published in 2011 in Security and Privacy. In DNS, this is even simpler, because you have a very distinct deterministic pattern which is created. And if the attacker collects sufficient number of copies of DNS databases from different vantage points, and then the detection can be actually very simple. So the question is, does encryption suffice, or should we do something more than that? Okay, so that would conclude my talk, and thank you very much. I'll take your questions now.
Right, so we have time for questions. While people in the room go to the mic, there's a question from Jabberland that says, from Elliot Lear, do you have initial thoughts about avoiding the TCP to UDP downgrade?
I'm typically thinking about attacks. That's actually, no. So there are different solutions to prevent downgrade attacks. And the question is, do we need to design something new, or can we take existing ideas? One of the problems with downgrade attacks, and it's a significant problem not just specific to DNS. Think about security updates. What happens when you cannot establish a connection to the Microsoft update server and you cannot patch a vulnerability? The attacker can prevent you from doing this in order to attack your system. The downgrade attacks are not specific to DNS. And this is an important and a critical issue in the internet. And actually, I will use this opportunity to advertise a paper which I'm working on with collaborators from Israel. And the paper has designed a basic building block which enables one to differentiate connectivity failures versus downgrade attacks. Attacker which drops packets selectively. Of course, attacker can always block entire communication, but the problem with that would be that the attacker would be detected. So the attackers, when they are able to, when they compromise the router, if there's a backdoor in the router or a proxy or something, they would be unwilling to give that capability away, so they will try to remain undetected. So the attackers would typically do low-rate attacks, which seem like connectivity problems. So we designed a basic building block using anonymity system, which enables one to detect failures versus failures on a link or on the way to the server versus connectivity versus malicious attacks, low-rate attacks by attackers. And how we do that? The idea is to use anonymity networks and to send sample queries to yourself and some to the destination server. And since the attacker will not be able...
Haya, don't give the entire paper away.
Okay, I'm not going to give the entire paper away, but the point is, so we considered this issue and we thought about it. Because this is a significant problem in the internet. There is no concrete solution currently. You can distribution of spam, distribution of blacklists, security updates, all of this, certificates requests, all of this is vulnerable to this connectivity versus failures versus malicious attacks, and it's an important problem, and that's what that we actually are proposing a solution for that, and I hope it could be used for DNS as well.
Once it's published, self-nominate for the ANRP
Thank
again.
You. I look forward to seeing you soon.
Stuart.
Hi, my name's Stuart Cheshire from Apple. You had a slide listing things like DNS Curve and other previous attempts to do DNS security.
Yeah.
I wanted to tell you about something that you may not have heard of, because a lot of people haven't.
Well, I said selected. I
Yes.
did mention that it may be that I may not have listed all of
So
them.
another small deployment of DNS over TLS was Apple's Back to My Mac service that started in macOS 10.5 about 8 years ago. And Lisha Zhang's and her students at UCLA very graciously documented that and wrote that up as an RFC. I think it's 6281. So if I mentioned that as another example of it wasn't internet-wide, it was only Apple-to-Apple customers, but it was another example of running DNS over TLS for the same reasons that we didn't want to reveal too much about the queries.
Thank you very much for pointing that out. Actually, I will appreciate it if any of you that is familiar with other defenses that were proposed. I'm actually in the process of studying all of those, and I will be very happy to receive a pointer to that. If you could email me, I will give you my email, and I would be happy to add that to the study. Thanks.
Yep. I guess I didn't say it clearly. The reason I mentioned it is it validates the work you're doing. It shows that we did care about that. It didn't cover all the attacks that you described, but we definitely thought it was important to try.
Thanks. Okay.
Alison.
Yeah, hi, Alison Mankin from VeriSign. Hi, I like this work very much. It's a great contribution. I'm looking forward to seeing more about the TCP work. I just wanted to mention that, I mentioned this to you one-on-one too, that a lot of the emphasis is sort of understanding the difference between the stub to the recursive and then the recursive to the authoritative. And there's a lot of, so that's what the standards development is mostly on right now. And when you do the recursive to the, when you have a stub to a recursive, it has the choice of going to a different recursive if it has a problem. So it could actually say, I can't get TCP here, I'll go to another, or I'll choose only a recursive that I know has good TCP, which it doesn't have that choice in the case of the authoritative. And similarly, there's some very different properties of the anonymity set that's exposed in the recursive to the authoritative than in the other. So that's been a useful distinction in doing this analysis, and it's probably worth thinking about as you continue this research.
Thanks, Alison. Thanks for the feedback. So this is a good point. Of course, there are different, so the stub can go to a different resolver, this solves the problems on the resolver side, on the client side, for resolvers which do not support TCP, or for resolvers which are behind devices that will block TCP and so on. Actually, this also frequently happens when you have firewalls or NAT devices which block TCP. This is correct. It doesn't solve the problem on the name server side, but correct. This is you can use a number of resolvers, and there were proposals for that. I think you mentioned this in your work as well, no? You mentioned, yeah. So you should see the work. I read it a few times actually. It's an excellent paper, very interesting. And the resolver could select a number of different instances. The stub resolver.
Ralf Weber, Nomnom. This sort of, I think it reiterates what Jeff Houston said, that DNS is a mess. So there's one question to that. Wouldn't it be better to actually make privacy on the underlying protocol and then just keep everything as it is, the mess that we have?
Underlying protocol, you mean the transport layer?
Yeah.
Yeah, so that's the attempt which indeed VeriSign undertook, and also Unbound. And I think main difference between the proposal of VeriSign and the Unbound is that whether you can use the standard port or you have to go to a different port. That's along with other efficiency improvements, but this would be the main one with respect to changing the infrastructure.
Are you saying that if we switch sort of to TCP, we wouldn't be able to do the measurements that you do anymore? Or do we have to get a layer even deeper?
So I think if you switch to TCP, currently you would not be able to obtain, and you configure your resolver to insist on TCP, you will not be able to obtain DNS service for many domains currently. And it may be the case that many clients on your network will not be able to access you because of their home routers and so on. So I don't think currently it's possible to insist on TCP or to insist on encryption. I think it's an important research direction, and I think the proposals are very important and interesting, and I think it's critical to investigate all these issues, how compatible the existing infrastructure with those proposals is, how much changes are required, and what is the work that one needs to do. But if we adopt all of this right now, today, this will be, this may create a problem, which of course in the internet is not possible and would create detrimental losses.
And a second question, you said that you could digest the questions of a client out of behind a caching resolver. What were the amount of caches and what was the cache hit rate that you had on that resolver? And was there a difference depending on how much you cached or not? And did you also consider prefetching?
Prefetching by the browsers, that's an excellent point. So this was done before, that's why I haven't explicitly addressed this. Prefetching, I think, was, people looked into that with respect to web. And of course, if you looked at the prefetching domain requests, this leaks also a lot, no doubt. So I mentioned this in the paper, but I haven't studied prefetching specifically how much it leaks. On the client side, as you mentioned, between the client and the resolver, I used three types of channels. One, well, actually two. One, timing, whether something is cached or not cached, and how long it takes to receive a response. And actually, this latency often identifies the name server that the query was sent to accurately, or the entire set. Of course, you have repeated multiple times. So in the wild, currently, I'm only running the attacks between the resolvers and the name server, the caching resolvers and the name servers, not between the clients and the resolvers. And in addition, another thing is that this timing information allows you to identify the name server, but not the query.
We need to be a bit faster with the questions and the answers because we're running out of time for this one.
Hi, Matthias Welisch, FU Berlin. Then I skip one question and leave one. In your analysis, you considered the first 50K Alexa domains. Did you also consider the tail? Because, I mean, with the 50K, you have a bias to CDN served names.
Yeah, so excellent question. Right now, I have, for some time, I have different vantage points which send request responses. I already received emails from some internet operators about what is it exactly that I'm doing. And there's some suspicious activity with machines from different countries which run queries. So I report on 50K because that was the fastest that I managed to finish, but we are studying all the DNS trees, not only the forward 50K. So, of course, includes top-level domains, IPv6, IPv4, reverse DNS trees, and telephony, and so on, because I'm interested in the general state of the art, and so that I can report the accurate findings. And by the way, if anyone is interested to host those databases, I won in Microsoft for our group Azure award, which allowed us to use a lot of their infrastructure. Thank you very much to Microsoft. And if anyone is interested to collaborate on that,
we need to go faster.
Then it would be great.
We are really out of time, so you still have 3 people, and I want them to get their question in. So if you can manage one sentence questions and 1 sentence answers without too many commas.
I'll use compression.
Hi, Petr Spacek. 3 words, DNS over Tor.
No, that's not a good solution, actually. I'll tell you why. Because there were attacks where NSA on the last node, on the anti-SIG node, injected spoofed responses. So that will not work. I thought about that.
That was a perfect exchange, by the way.
Okay.
That's it. No, I was just following Lars's request. You see how compliant I am?
No.
Benno Overein, NL Labs. Not a question, a small remark. Indeed, Unbound uses a special port. During the hackathon this weekend, Sarah Dickinson...
Oh, you updated it.
And
should have told me.
We solved it. No, not solved it. Sarah Dickinson and Daniel Gilmer worked on a general TLS support.
Excellent, thanks. So I correct myself, it was solved. The Unbound uses a standard port.
Doug Otis, Trend Micro. Have you considered the impact of doing encryption over things that are very time sensitive like DNS? And I've been looking at how to solve that using something along the lines of, say, the QUIC protocol that Google's developing. That looks very promising from a solution prospect. Have you looked at that? That's
an excellent point. I am looking currently into congestion control mechanisms of TCP to identify which would be, there was a reason I mentioned this TCP version, that would be most suitable for DNS. And the question, of course, would depend whether you use the TCP connection just for one query or what the proposals for pipeline queries.
Well,
but specifically,
QUIC runs over UDP, by the way.
QUIC runs over UDP? No, so QUIC, I'm looking at the TCP proposals only currently, not for UDP, but these are good suggestions, I'm not saying not. I'm pro using UDP and DTLS, of course, but just recently started, I haven't got to that.
Great.
Stefani, questions?
We don't have time for questions anymore, I'm sorry.
Look, I was looking for it. Do you know for how many years?
Well,
Okay, good. Okay,
all right.
thank you very much.
Thank you very much, Haya.
Thanks.
So our next speaker is Joao Luis Obrinho, who has a paper on another big old piece of infrastructure, the BGP. This was published at ACM Conext last year. Congratulations on the prize.
Well, good afternoon. It's a pleasure to be here. My name is João, and I'm going to talk about distributed route aggregation as means to scale the internet routing system. The talk reflects joint work with Laurent van Bever, Frank Ley, and Jennifer Wexford. Well, news from August last year came to remind us that the internet has a routing system, that the internet routing system is engineered and has limitations. So in August last year, the number of globally advertised IPv4 prefixes went past the 512K mark, which was the default forwarding table size of some routers. These routers could not cope with all the routes they were receiving, which event caused some noticeable degradation on the internet. Okay. As a matter of fact, the internet routing system does not scale well. So the internet comprises some 50K networks called autonomous systems. Each network has address space, normally summarized in a number of IP prefixes, and most of the IP prefixes originated at an AS are propagated by the Border Gateway Protocol to all other ASs. So for example, prefix 1000/16 originated at AS4 is propagated to all other ASs. The same is true of prefix 1100/16, which is originated at AS5 is propagated to all ASs. And even prefix 1010/24, whose address space is contained in the address space of the less specific prefix 1000/16, ends up being propagated to all the internet. Take the analogy, however crude it is, with road networks. A prefix is a set of addresses, could be a neighborhood in a city. Internet-style routing in road networks would imply that every crossroads in every city would have a signpost for every neighborhood in the world. This is not realistic for road networks, and it takes, in terms of the internet, it takes a toll on performance or cost. Okay, so the growing number of globally advertised IPv4 prefixes overloads the forwarding tables of the routers, and the time it takes to look up an address in those tables. It overloads the routing tables, it increases the setup time of a BGP session, and it affects the churn, the convergence time, and the overall stability of the internet. It also, the lack of scalability also does not bode well for the future of the internet routing system. We are finally witnessing a transition from the 32-bit IPv4 prefixes to the 128 IPv6 prefixes. Without an addressing plan for IPv6 that takes routing scalability into account, many more IPv6 prefixes are potentially formed than IPv4 prefixes. At the same time, we see a momentum towards endowing BGP with security features. Secure BGP in particular requires signing and authenticating and validating routes in real time, and that takes a burden on the routing processes. So Dragon is our distributed solution to scale the internet routing system. The basic Dragon allows for savings on the order of 49%, well, 50% savings on the amount of routing state. Full Dragon will allow savings on the order of 79%. Okay? I will tell you the difference between basic Dragon and full Dragon in a minute, but let me just say that at this moment that Dragon does not require any changes to BGP, to the BGP protocol. So the routing messages are the same routing messages as the BGP protocol. Okay? Does not require changes to the forwarding plane. You just need to upgrade the router software to take our rules into account. Okay. So in the remainder of this talk, I will present Dragon. I think much of the science and the art of inter-domain routing lies on the ability to establish relationships between global routing behaviors and local routing decisions. So I'll start with the global view of internet routing scalability, and then I will present Dragon. So the basic Dragon has a filtering strategy, full Dragon has as well an aggregation strategy. Okay? I will also show you some performance results later on. So the global view, at a very high level, the idea is to propagate the more specific prefixes, the longer ones, only in the vicinity of the ASs that originate those prefixes. So in this example, you have prefix 1010/24, whose address space, the address space of which falls into the address space of 100/16. That prefix is is originated at AS3, is announced to AS2, but not to AS1. Okay? In terms of forwarding, it means that data packets are forwarded along ever more specific prefixes until they reach their destinations. So in this example, I have prefix with a destination address 1011, arrives at AS1, it matches prefix 1000/16, it is sent to AS2, but when it arrives at AS2, it is forwarded along the more specific prefix 1010/24, which then delivers it to the destination. This more closely resembles what happens in road networks, where crossroads have signposts with coarse-grained information about faraway destinations and detailed information only about nearby destinations. So one question we might ask is this reasonable to implement in the internet? Well, in hindsight, after the work that we did on Dragon, we believe that the answer is yes. There is some implicit structure in the internet routing system which can be exploited for scalability. There are two aspects to this structure. First, many ASs buy connectivity to the internet, access to the internet, through providers. And this establishes an hierarchy among the ASs, where the providers are on top of the customers. It turns out that this hierarchy is aligned with the prefix hierarchy, in the sense that the more specific prefixes are typically announced, are originated by customers, somehow suggesting that these prefixes don't have to be announced too far away from the provider of those ASs. The second rough structure of the internet is the fact that ASs with aggregatable address space tend to be close together. ASs acquire address space from routing information registries, which allocate space in a given geographic region, and ASs tend to connect to providers in the same geographic region. This is rough. This is not mathematics, exact thing. So this gives an intuition why this is going to be possible. So the big question for us now was, how do I realize this global view of advertising the more specific prefixes only in the vicinity of the ASs that originate them with automated local routing decisions? Okay. And this is challenging because the internet is as decentralized as it can be. Each AS decides where to connect, whether to peer at an internet exchange point, whether to multi-home, where to acquire address space from a provider, from a routing information registry, how to announce my address space. Do I deaggregate many prefixes? How do I treat the route that I receive from my neighbors regarding other prefixes? So all this is very decentralized. So Dragon is our set of rules to implement the global view, to scale the internet routing system. First component is a filtering strategy, which allows nodes, ASs, to filter some prefixes while respecting the routing policies. So filtering a prefix means that the prefix is not installed on the forwarding tables of the routers, and the prefix is not announced to the neighboring nodes. Okay? With filtering comes a concern, which is the concern of black holes. I filter something is not there. Data packets might arrive at a certain AS with a destination address which does not find a matching prefix in the table. That is called a black hole. The packet will be discarded. Provably, Dragon does not have black holes. And it aligns with the incentives of the ASs. I will assume that among the incentives of the ASs are the will to save on forwarding state and the will to forward data packets along the best possible route as dictated by the routing policies. So nothing different here. Routing exchange is a standard BGP. So I'm going to give you an example in this mini internet of the filtering strategy. This mini internet has 6 ASs. The lines represent adjacencies. A solid line represents a provider-customer adjacency with a provider always above the customer. A peer-peer line represents a dashed line represents a peer-peer adjacency. Okay? So AS1 and AS2 are peers. AS1 is a provider of AS5. AS3 is a provider of AS5 and AS6. Now let's suppose AS4 acquired some address space, which is summarized by a prefix P, and that AS6 bought some address space from AS4, and that address space is summarized by prefix Q. So prefix Q is more specific than prefix P. Let's see how prefix Q is propagated throughout the network. So AS6 creates a route. A route associates an association between a prefix and an attribute. Attributes in the general sense of a property of a path, not necessarily BGP attributes, although I could map them into BGP attributes. But creates a route. It's going to send it to its neighbors. What do the neighbors do with that? Well, I will assume the Gao-Rexford routing policies, which are accepted as a baseline of understanding of interdomain routing. So these policies are based on just 3 attributes. The route is learned from a customer, learned from a peer, or learned from a provider. The preference among routes follows the flow of money. So if I have a customer route, a peer route, and a provider route, I prefer the customer route because the customer is paying me. Second, I'm preferring the peer route because the peer is not paying me, but I'm also not paying to the peer. And then I prefer, last, a provider route. I'm paying to the provider. Okay? The exportation of routes also follows the flow of money. So customers buy connectivity to providers, so providers announce to the whole internet all the routes they learn from the customers, and they send to customers all the routes they learn from their neighbors. So let's see this in operation here. Q route is a route pertaining to prefix Q. So the routes sent by AS6, they reach AS3 and AS4. They elect a customer route, this is cust here, customer route, and they announce to their neighbors. This is the rule. Okay? So AS2 receives routes from AS3 and AS4. It elects a customer route as well. It can reach Q via customer. It sends a route to its peer, AS1. AS5 learned a route. It elects a provider route from a provider, has no one else to send the route to, so it ends there. AS1 elects a peer route and even sends a route to AS5. So the final state for this prefix Q is such that AS2, 3, and 4 elect a customer route to reach Q, AS1 elects a peer route to reach Q, and AS5 elects a provider route to reach Q. A similar process will propagate prefix P throughout the network. Now, after doing this, propagating, I will arrive at this state. So the state contains the type of route for Q and the type of route for P, with less specific prefix. So for example, AS3 elects a provider route to reach P. So to reach AS4, it has to go like this. But it elects a customer route to reach 6. It goes like this. Okay? Forwarding is dictated by the longest prefix match rule. So a data packet is forwarded along the prefix, the most specific prefix that matches the address, the destination address of the data packet. So a data packet arriving here to AS3 will be sent directly to AS4 because it matches this Q. Okay? Now the goal of Dragon here is to dispense with Q as much as possible without violating the routing policies. And I will work with this filtering code. It's one of many possible filtering codes. Other than the origin of P, in the presence of the prefix P, the less specific one, I can filter the more specific one, provided that the attribute of the P route, the less specific route, is the same or preferred to that of the Q route. So the checks there mark the ASs that can filter Q according to this filtering code. For example, AS2 elects a customer P route and a customer Q route. It can filter Q. Okay? This makes intuitive sense. This makes intuitive sense from the point of view of a sigla AS. On filtering, I save on the forwarding state. And then if I filter Q, data packets with destination in Q will be forwarded along P, but P has the same or even a preferred attribute. So I'm equally good or better. The point is, this makes sense from the point of view of a single AS. But what's the global consequence of that? What's the consequence on the other ASs of doing this filtering? So let's suppose that AS2 does filter. If it does filter, it cannot send a Q route to AS1. So AS1 is in fact oblivious of Q. But it still sends data packets to its peer along the P route. So when AS2 filters, AS2 saves on forwarding state, and AS1 becomes oblivious of Q, meaning that it saves on forwarding state and on routing state. Let's suppose that all ASs apply the filtering code. If all ASs apply the filtering code, then we arrive at this final state, in which you can see that AS3, 4, and 5 have detailed information about Q. They have information about Q. But AS1, 2, and 5 only have coarse-grained information about Q. That coarse-grained information is P, prefix P, which is less specific. Okay. Another way of looking to this, going back to the global view, is that the Q is propagated only to 3 and 4. It's not propagated further in the internet. I'd like to call your attention to two aspects, two global properties of this final state. The first one is correctness. I mean, no packets are lost. There are no routing anomalies. Okay? Packets are not black holed or trapped in a loop. The second property is route consistency. The attribute of the quality, if you would, the attribute of the route used to forward data packets is preserved after filtering. Such a state is called route consistent. So before filtering, AS1 sent data packets with destination in Q along a peer route to this peer. Now it still sends them according to a peer, although following the P route, not the Q route. Okay? And the same is true for all of them. Moreover, this state is optimal route consistent. No other AS can filter Q there without violating the condition of being route consistent. If AS3, for instance, filters Q, it will start sending data packets according to the P route, but the P route sends them up to AS2. Okay? So it violates route consistency. Okay. It's not likely that all ASs will deploy Dragon, the filtering strategy of Dragon at the same time. I would like to show you one example highlighting two aspects of Dragon in partial deployment. The first one is the following. One AS filtering incentivizes other ASs to filter as well. The second aspect is that there is an order for deployment of Dragon which is route consistent at all intermediate stages of deployment. So it's almost like substituting the wings of a plane while in flight. We'll see that. First, a different example. AS2 is a provider of AS4, which is a provider of AS5, which is a provider of AS6. AS2 peers with AS1 and AS3. AS1 is a provider of AS3 and AS6. The combined state is represented here. AS4 in particular elects a customer route to reach Q, which is originated here, and a customer route to reach AS5, to reach P, which originated here. According to the rules, the filtering code, AS5 can filter. Let's suppose it does filter. Well, I'm not very good at that. Okay, let's suppose it does filter. If it filters, it no longer sends a route to its provider. So AS2 before elected the customer route, and now it elects a peer route via AS1 to reach AS6. Okay? But now the interesting aspect here is that AS2 has a double incentive to filter as well. On filtering, it saves on forwarding state and reverts to sending the data packets with destination in Q to its customer AS4 along the P route. Okay. So the point was, so the arrow, the green arrow representing the flow of data packets goes downwards again at AS2 after AS2 filters as well. The point was, filtering by one AS incentivizes other ASs to filter as well. Let's go back to the initial state and to show you that there is an ordering for adoption of Dragon that is route consistent at all intermediate stages. And in the specific case of the Gao-Rexford routing policies, this ordering is the following. Nodes that elect a provider of peer route should be the ones to filter first. So the one that elects a peer route there for Q is 3, should be the one to filter. If it filters, it still sends data packets to AS2. The flow is the same. Then, ASs that elect a customer route, they should apply the filtering code top-down in the hierarchy. So an AS should only apply the filtering code after its providers have applied the filtering code. So rather than being AS4 and then AS2 applying the filtering code, it should be the other way around. So AS2 is the first, the flow of data packets, so the green arrows remains the same, and then AS4, and the flow of data packets remains the same. Well, we don't have just 2 prefixes in the internet. We have more than 512K prefixes. These prefixes are logically organized as trees with the provider-independent prefixes at the roots. Provider-independent prefixes are those that were allocated directly from the RIRs. Okay? Dragon applies by contrasting a prefix to its parent prefix in a tree. The parent of a prefix is the most specific prefix that is less specific than the prefix in question. Okay? We can show that the Dragon is correct in the sense of not creating routing anomalies for all the routing policies for which BGP works correctly. And we can also show that we have route consistency, both optimal route consistency and route consistency through partial deployment, if routing policies have a property which I'll call here isotonicity. Okay? Includes the Gao-Rexford routing policies. Isotonicity would be a talk in itself for how it relates to routing. But in a sentence, it means that if an AS prefers route A over route B, a neighboring AS does not have the opposite preference after processing of the routes, of the 2 routes. So it's I also would like to make a sort of note here that the fact that it's route consistent does not say that many AS forego the prefix queue. It does not say that it's very efficient. It's optimal, it's the most that you can do, but it's not necessarily very efficient. We'll go to that in a moment. Well, the provider-independent prefixes cannot be subject to filtering because they do not have a less specific prefix in the routing system. Okay? So Dragon has an aggregation strategy which allows ASs to generate less specific prefixes on account of which the provider-independent prefixes can be filtered elsewhere in the network. Aggregation prefixes satisfy some rules. They are sort of beacons. They are not final destinations. You cannot create address space with them. Okay? So it does not create address space, allows filtering of provider-independent prefixes. And there's an interesting aspect as well, which is if more than one AS decides to generate the same aggregation prefix, BGP self-organizes and finds the best ones, automatically finds the best ones. Well, where should I point this? Me neither. It's yours. Yeah, okay, sorry about this. I think this is the next slide. Okay, I will only go to a very simple and simplistic even slide about the aggregation prefixes. So AS1 is a provider of AS2, which is a provider of AS3. AS3 is a provider of AS4, AS5, and AS6. Okay? AS4 owns prefix P0. So this is prefix P appended with a 0. AS5 owns prefix P10, and AS6, P11. So the combination, the global address space of P0, P10, and P11 make prefix P. Now AS3 elects a customer route for P0, P10, and P11. Thus, it can create an aggregation prefix P. It does not create new address space. It's already there on the account of P0, P10, and P11. It covers at least 2 of those prefixes, and it elects a customer route for all of them. So if AS3 indeed creates, as an origin, prefix P, this allows AS2 to filter P0, P10, and P11. And AS1 will be oblivious even of those prefixes. Okay? The other ASs below, AS4, 5, and 6, will also be able to filter some of the prefixes. Okay, in general, the aggregation prefixes apply on top of the parentless prefixes in the internet routing system, so the provider-independent prefixes. The system self-organizes if more than one node generates the same aggregation prefix, and we can even show that for isotone, this property of routing policies, if they have them, it finds the optimal origins in the sense of maximizing the filtering possibilities of other ASs. So let me just go quickly through some performance results. We computed the filtering, we could evaluate Dragon along many different dimensions. I've chosen here the fib filtering efficiency, the amount of reduction that you have in the fib. We used, for our computations and our simulations, we have used the annotate topologies made available by CADA. which have about 50K ASs, 94K provider links, 94K customer links, 180K peer links. We also use the files that have the IPv4 to AS mappings provided by CADA, which account for about 530K prefixes, 270 of which are provider independent. Again, there are many metrics that we have, even in the paper. We just selected here the normalized amount of reduction brought by Dragon to the forwarding tables of the ASs, so the FIB efficiency, let's say. Basic Dragon just consists of the filtering strategy is such that every AS can filter at least 47% of the prefixes. And 87% of the ASs can reach the maximum filtering efficiency of 49%. If you put aggregation prefixes on top of that, then every AS can filter at least 69%, can have a filtering efficiency of at least 69. And 87% of the ASs, again, the number is the same, have a filtering efficiency of 87%. I'm sorry, of 79%. So 87% of the ASs have a filtering efficiency of 79%. That's what I meant. In conclusions, so Dragon is a BGP add-on to scale the internet routing system. Dragon can be deployed incrementally in today's internet. Reduces the amount of forwarding state by approximately 80%, forwarding and routing state by approximately 80%. But from my point of view, Dragon is, even more fundamentally, is a solid framework to reason about route aggregation. So it's based on solid theory on routing that identifies routing as having many, routing as done in BGP, two components, a selection and the propagation of routes from one node to the other one. So this is based on a solid theoretical framework, which should provide a way to reason about route aggregation. Thank you. I'll accept any questions, of course.
If there are questions from remote, put them in Jabber and I'll relay them.
Stuart Cheshire from Apple. There are a lot of smart people working in routing and a lot of big companies with a lot of money involved. Do you have any idea why they didn't come up with these ideas earlier?
In a way, that's a question that you should make them, not to me, right?
If anyone from those companies wants to come up to answer,
it's a good
feel
point.
free.
It's worth thinking about it. I don't know why. But we did look, we did look around in many places to see if something similar had appeared. Maybe someone in the audience has some...
There might be a combination of commercial and technical reasons. Because, when from a vendor side, as previously working for a networking vendor, the point is that you are coming with commercial restraints from the company as well as from your from your customers. So you are not always deploying the best technical solution because you're doing you're making a compromise between the technical and commercial.
Thank you.
We may not get an answer to that question here and now, but thank you for this good work.
Thank you.
Hi, Carlos from LACNIC. This is really cool. We've toyed with similar ideas in the past, different places that I was working, similar, in a way similar to this. I'm curious about two things. One is, where would be the proper place within AAS to run Dragon? Border routers, route reflectors, where would you run Dragon? Everywhere. And in some cases, within your AES, you need to keep your more specifics because the more specifics are used to do traffic engineering by your downstreams. So the ideal scenario is you keep the more specifics from your customers and try to avoid propagating them to the whole world who doesn't care about them.
Okay, so that's a very open question. Thank you very much. Let me just first say the following. This sort of way of thinking, I presented at AS level, but it could be presented at the router level. So you could also do route aggregation inside an AS and see what the prefixes are needed there, not needed there. Except that inside an AS, you normally do shortest path or variations of this, and there you might have some stretch. You cannot really filter too much without losing some quality of the routes. As to the first question, that's also a good point. I would say that it would be on the border routers that you would start to implement that. But we have to make the study as well, yet. It's not done.
Thank you very much, and thank you for this.
Let's jump to the other queue on the left.
Oh, I'm sorry.
Hi, John Mitchell from Google. Thank you for this work. It looks like really interesting work. Have you considered the differences between this and 6769 simple virtual aggregation, like especially on your comparison of how much fib reduction can be achieved?
Could you please repeat the
RFC number 6769 is on simplified virtual aggregation. It's a fib-only technique, doesn't reduce the propagation to other ASs, but I'm curious about the efficiency study of this versus that.
It's very similar. The filtering efficiencies are very similar. Let's say that Dragon is a sort of distributed computation, one for all of them, rather than replicating the computation at every router or at every AS. But the results are very much similar. The assumptions are slightly different. So they, normally in FIB, they can aggregate if the forwarding neighbors are the same. And here we aggregate if the quality of the route is the same. But you could also improve this, or change this filtering code to take into account forwarding neighbors as well.
Yeah, so just a quick comment on a previous question related to simplified virtual aggregation. There's a question, I assume you realize, I don't know if you've spoken with any vendors about implementations, but one of the challenges with simplified virtual aggregation that also appears to apply here is that even though your lookup engine, of course, optimizes for more specifics, the BGP process on many vendors may not have that concept because more specific and an aggregate isn't a concept that BGP itself needs to understand. So when you get a withdrawal for an aggregate here, you have to do special optimizations for the more specifics that it was being covered by now, whereas in standard BGP, you don't need to do that. So this is a fairly large rewrite to BGP for some vendors. I would just point that out.
Let's go to the back queue here.
Hi, Matthias Welisch, FU Berlin.
Just a bit louder, please.
Just an operational comment that relates a little bit to the comment by Carlos. If you filter out all more specific prefixes, you might conflict with security solutions such as the RPKI. For example, if the more specific is covered by the RPKI, but the less specific not, then you include the not secured prefix and compared to the not secured and the secured prefix.
Okay, the question was about ROAS and RPKI at least, right?
It was not a question, it was a comment. I mean, if you filter out
for the comment.
all more specific prefixes, then you might conflict with these security solutions. In particular, if the more specific is secured and the less specific is not secured.
Right, right. If you have RPKI, you can have different sort of combinations between being secure, not secure, the prefix and the parent prefix. And in case that the more specific prefix is secure and the other one is not, maybe you would not filter.
Yeah, you shouldn't.
Just because we're jumping between the queues doesn't mean you need to sit down. So you get your turn. I just try to do it sort of round robin if I can. Ken.
Ken Calvert, University of Kentucky. This is great stuff. I wanted to mention that we had done a measurement study about 5 years ago. It was a GlobeCom 2010 paper. And we wanted to ask the question, how much are we losing, to what extent is hierarchical address, how inefficient are current address assignments? In other words, how close to flat is it, or how close to really topologically based? And our result, we used very similar aggregation rules, and our results are very consistent with yours. We found it was about a factor of 2 to a little more than 2. So I'll send you a pointer to that. And I'd like to talk to you a little more about the aggregation rules are actually in BGP right now, right? That you're not adding anything to the protocol, right? It's just that most routers don't actually do that at this point. Is that correct?
You're probably right. There is one thing, Ken, which is to generate an aggregation prefix, I have to be sure that I'm not creating new address space that's not there.
Right, and I should say that was what we did. We said if we started from scratch and assigned addresses in a topologically based way, how much would we save? And we didn't measure it exactly the same way, but it was very close to your result.
Okay,
thanks.
Sandy Murphy, Parsons. I had a question related to your aggregation example, and I'm not certain whether it's covered by your creating new address space question. Is there anything in your work that, that ensures that the aggregation is in some sense minimal? That you're, if you have P1 in your P0, P10, P11 example, if the guy's not connected to the P10 customer, but he aggregates P0 and P11 and produces an aggregate of P without being connected to part of that address space.
Then it would break.
That
would break the protocol. That could create packets going to some place that is lost. They're lost.
Right.
So
Is there anything in what you're doing that would prevent that from happening?
well, at least a node NAS can detect locally whether or not it can aggregate. It has to have all the address space covered.
Right.
If it
Okay,
doesn't, it shouldn't
so
aggregate.
Sandy Murphy, Parsons, working group chair, co-chair, and the CIDR working group, what you're saying is there's no way to ensure that the aggregator has the right to be producing that aggregate, which means he can invent anything.
Well, probably. Well, you almost sound like a lawyer. You are saying that. Anyway. Are you addressing security features? I mean.
Yeah.
Okay, right. That has to be addressed. This is not being addressed here at the moment. So someone would have to create a row, let's say, for these aggregation prefixes. There has to be some security
Which
system.
I understand, but if there's no direct connection between P0, P10, P11, and the guy producing the aggregate, you know, the things about proxy aggregation that have appeared in forever and ever and ever, the problem is if it's some far away point, the people at the end don't know who's doing the aggregate. They can't produce a ROA unless they know who it is who's going to be aggregating.
Right. These aggregation, well, that's an open question.
Yeah.
I don't have the answer for that. But these aggregation prefixes are generated higher up in the hierarchy. So it's not the stuff in the small networks. So maybe there are more trusted parties. Maybe, or through a third party, they can become trusted. Through, let's say, through RIR, for instance, which could perhaps allow some trusted AS to...
So I've asked you a question you don't have an answer for. I don't want to have to make you do extemporaneous on the spot inventing a solution here.
No, we thought briefly about it, but we know that there are challenges with the security of the aggregation prefix in particular.
Okay.
But the filtering strategy works in today's internet. That's why I separated basic Dragon from full Dragon.
Yeah. Okay. Thank you.
Thank you.
Actually, thinking about this for the applicability of the Dragon, it's could be very interesting for intra single operator for BGP-enabled services. Because as you're building BGP-enabled services, you have multiple address spaces, how you can aggregate that. And then as a single operator, you can start creating some very interesting prefix hierarchies that you can have a more efficient deployment of services as essentially as your overlay networks on top of your existing infrastructure. And because what you're trying to do is you're limited by the pretty small fibs of the devices where most of your services are residing. And then this is one of the questions, how to reduce that. So not just from a global perspective, but as the new services are being built, that could be an interesting application.
Thank you.
All right, I could have sworn there were more people on the mics earlier. So if you have a question for Joao, now's your chance. I don't see anything in the Jabber room either. All right, thank you very much. Hi, and Joao, if you could stick around a little bit, I think ISOC wants to do a quick video with you afterwards. If you guys want to see more good talks like this, nominate papers for the ANRP for next year. Otherwise, we're running out. See you in Yokohama unless anybody else has anything IRTF related that we didn't cover yet. All right, you're first in line for cookies. Thank you.
Thank you for your Yes, you have a web page.